let's take a look at an exponential equation where half-life is involved. So I'm going to use the example of caffeine. It has a half-life of about 6 hours. So what that means is every 6 hours, half of the caffeine that was in your system is now gone. So let's suppose at hour 0, we have 100 milligrams of caffeine in our system. If the half-life is 6 hours, that means 6 hours later, there should be only 50 milligrams left. And in another 6 hours, so 12 hours from the initial caffeine intake, we should be half again, which should be 25 milligrams, and another 6 hours later, so 18 total, should give us half of 25 or 12.5. That's what the half-life means. And we can turn that into an equation if we make the observation here that, every 6 hours, we have half of what we started with. So on one side, we're looking at groups of 6 hours. On the other side, we have a multiple of 1/2. 1/2 times over and over, provided we had that change of 6 hours on this side. So putting that together, we get an equation that looks something like this. So if I say Y is my caffeine, then Y would be starting at 100 milligrams. We're going to cut that in half every 6 hours. So I take the total number of hours and I divide by 6 because I'm looking for groups of 6 hours. So there's one group of 6 hours, two groups of 6 hours, three groups of 6 hours. And you think about it, right? 18 divided by 6 is 3. And to get that 125, I had to multiply 1, 2, 3 times. So that 12.5 right there could be expressed as 100 times 1/2 to the power 3. 18 divided by 6, because we're looking for groups of 6, gives me that power of 3. Now, taking this a step further, often when we're talking about exponential change, we look at a percent increase or a percent decrease. Well, this is a decrease, so let's see if we can find the percent decrease. So, let's see, I can't see my new page button. There it is. Okay. So I have the equation 100 times 1/2, parentheses are necessary there, raised to the power of time, hours over 6. Oftentimes we have equations that look like that starting times 1 plus some rate to the power of t. And since this is a decrease or a decay, r should be negative. Now, to try and figure out what that r is up here, I just consider that right there. And I'm just going to rewrite that a little bit as 1/2 to the power 1 over 6 raised to the power of t, or times t. Okay? So dividing t by 6 is the same as multiplying t by 1/6. That's what I have there. And the interesting thing about looking at it that way is I can just plug that in my calculator right there. So let's give that a try on the calculator. So I want parentheses 1/2 raised to the power of parentheses, because it's complicated, 1/6. So 1/2 to the 1/6, according to my calculator, is about 0.8909 if I went to 4 decimal places. 8909. So my calculator says this base here is approximately 0.8909, and that power t is just hanging out there like that. So now comparing this right here to a possible base of 1 plus r, 1 is 100%. So, what was subtracted here? Well, I just compare those two by saying, well, 0.8909 must be equal to 1 plus r. So let's take away 1 to get r. So r would have to be that. Oops. -1. calculator, take away 1, I get a drop of about 10 or 11%. So let's go to 4 decimal places again. So R is 0.191. And it's a negative, right? A decrease, a drop, which we could say is about negative 10.91%. So anytime we have a half-life, we can turn it into a percent decrease. Anytime we have a percent decrease, we could also turn it into half-life. That's it for now.